Hi everybody. In this video I want to go over some stuff related to dynamics, so forces and Newton's laws, and kinematics, so how we represent motion mathematically, and the connection between those two topics. So let me start off by just going over Newton's laws of motion. The first law tells us that if we have a object moving with no net force on it, then the object will move in uniform motion. It'll have zero acceleration and constant velocity. The second law is the one that relates the force to the acceleration on an object. So the second law tells us that the net force on an object is equal to the object's mass times its acceleration. And then the third law tells us about interactions between objects. It tells us if we have two objects, A and B, and if A is exerting a force on B, then B has to exert a force on A, which has the same magnitude but is in the opposite direction. Okay. So, in the context of electric charges, this means that, when we have two electric charges, they're always exerting equal and opposite electric forces on each other. Okay, so how do we actually use this? Well, what we'd like to be able to do typically is write down Newton's second law and use that to find the acceleration of an object. Now, that's only really going to work if we have a net force that is constant, in which case we get constant acceleration motion. In the more general case, we write down Newton's second law, we get a differential equation that we would need to solve to find the motion of our object. Okay, what if we don't have a constant net force? So an example of that you might be familiar with is with the spring force, where the force depends on the displacement of the spring. Right, in that case, we don't typically study that motion using, Newton's second law in kinematics, at least in physics 5a. If you've taken physics 5b, then, you might have seen that you can write down a kinematic formula for motion with a spring. But at least from the 5a point of view, we're really only dealing with constant acceleration motion. Okay, and so what's the procedure for actually doing this? Well, the first thing we need to do is identify all the forces on our object and draw a free body diagram. Okay, so you always want to draw a free body diagram. That's going to help you organize the forces that you have. It'll show you the directions you're pointing in, the directions that the forces are pointing in. And that's important because you're going to need to decompose the forces in order to use Newton's second law, right? Once you have your free body diagram drawn, then you need to choose some coordinates and decompose the forces. Okay, so let me just give you an example of this, right? Let's say this is our object that we're looking at, and we have whatever. I'll just pick some random forces. F1, F2, F3. So this would be our free body diagram. Right? And then I want to choose an x-axis and choose a y-axis. And decomposing these forces like we talked about in the vectors video, right? I would, draw right triangles for each of these forces, figure out the x and y components. So I'd get F1x, F1y. I'm not going to write out all the components, but you get the idea. F2x, F2y, etc. Right? And then Newton's second law says it's a vector equation, so I have two equations, one for each set of components, right? I would add up the x component of F1 plus the x component of F2 plus the x component of F3, and that's equal to the mass of our object times the x component of the acceleration. And the same thing for the y component. Okay, and then from here I could solve for the acceleration, right? This is a relatively simple example. We just have one object. We know all the forces on the object. We don't have any constraints or anything. We could just set this up as an equation that we could solve for the components of the acceleration. Okay. And this is really as complicated as this stuff is going to get from a 5C point of view. Okay, so then once we have the acceleration, what do we do with that, right? How do we study the motion of an object, of a particle? Well, for that we can use kinematics. Right, which is how do we represent motion mathematically? And the starting point for this is we have a particle that has some position, right? And we have, we've chosen a coordinate system. We have a particle. It's got some x position and some y position. Okay. And we can, so these are going to be functions of time, the components of the position, x of t and y of t. And then we can define the velocity. So the velocity is a vector that tells us how our particle is moving. All right, the position tells us where our particle is. If I can select this, there we go. The velocity tells us how is the particle moving. Okay. And the velocity is a vector. Okay. It's got components v sub x and v sub y. That's why I drew it in this picture as an arrow, right? And these components are the derivatives of the position coordinates. So dx dt and dy dt. Okay. As a reminder, you can think about these derivatives as the slope of the tangent line to the respective position graphs. So, for example, dx dt is a slope of the position versus time graph for the x component, and same thing for the y component. Right? Okay. As another reminder, the magnitude of the velocity is called the speed. Okay, and then finally, the last kinematic quantity we need is the acceleration. That tells us how our motion is changing. And that's the derivative of the velocity. Okay, so the components of our acceleration vector, ay and a sub x, right, those are the derivatives of the velocity components. All right, now when we talk about kinematics in a physics 5a context, we're pretty much always referring to constant acceleration kinematics. Right, so if we have constant acceleration, then I can work out formulas for the position and for the velocity, which as functions of time. So I can get this formula for the position. Okay. I could write down a similar formula for the y component, okay, but you can just, replace all the x's here with y's and you get an equation for y of t. The x naught here, this is our initial position. So the position at time 0. V naught x is the x component of the initial velocity. Okay, and then a sub x is the x component of the acceleration. Right, and this thing here, this is v sub x at time 0. All right, so if we write down this equation, if we know the initial position, if we know the initial velocity, if we know the acceleration, we can find where our particle is at any time after t equals 0. And if I plot this thing as a function of time, if I look at a position versus time graph, then I get a parabola. Okay, depending on the sign of the acceleration, it's either going to be a concave up or a concave down parabola, but we know it's a parabola because this thing is a quadratic function of time. Right, so the fact that the slope of this graph, remember the slope is the velocity. So I could look at the slope at each point. That tells me what the x component of the velocity is at each point in time. And the fact that the slope is constantly changing, right? The reason for that is because we have this constant acceleration. The acceleration tells us how our velocity is changing. I can write down the velocity equation in constant acceleration motion as well. Okay, that's this equation. This is just a linear equation, right? So if I plot v sub x as a function of time, I just get a straight line. The slope of this line is our acceleration. Okay. There's another kinematic formula which I can get by eliminating time from these two equations. So I could solve for time from one of them, plug it in the other, and I get this other kinematic formula which says the square of the final speed is equal to the square of the initial speed plus 2a sub x delta x. And, when you first take physics 5a, this is presented to you as a kinematic formula, but later on in the course, you see how this is actually a consequence of energy conservation. Right? This comes from it comes from the work energy theorem, right? So it comes from relating the change in the kinetic energy to the work. The work is related to the force, which is related to the acceleration, so that's how we end up with this. Okay, so I want to mention just a couple special cases of constant acceleration motion. One case is uniform motion, which is the case of constant velocity. Okay? So, in other words, zero acceleration. If we have no acceleration, now we can still use these formulas here. We just have a sub x is equal to 0, right? So I would have my x of t is x naught plus v naught x times t, and my vx, well, that's just constant, right? In this case, my position versus time graph is just a straight line. Okay, something like this. And the slope here is whatever our velocity is, right? Our constant velocity. Okay. So for this particular case, for the case of uniform motion, if I want to calculate what the x component of the velocity is, I can just take rise over run, right? That's not true in general. If I have an acceleration, then v sub x will not be equal to delta x over delta t. I would have to write it as dx dt. Okay, this is always true. All right, another special case is freefall motion. That's motion with gravity. Right, and let me start here from Newton's second law. Right, so we have let's say we have an object moving under the influence of gravity. So the net force in the y direction, the big minus sign, is the weight minus mg. That's equal to m times a sub y, and that tells us a sub y is equal to minus g, right? Remember, g is 9.8 meters per second squared. So this is constant acceleration motion. I have acceleration minus g in the negative y direction. And in this case, I can write down my position and velocity equations in the y direction depending on my gravitational acceleration g. Right. So here I get a position graph. Well, it doesn't have to be negative. I get a position graph that is concave down because I have a negative acceleration. Right, and I get a velocity graph that is a straight line with a negative slope. Okay, I think that's all I want to say about Newton's laws and kinematics. If there's anything else about this that you would like me to review, please let me know. But I think that's the extent of what you'll need to know for this class. If you have any comments, any feedback on this, any other videos you'd like to see in the future, please let me know. Thank you, everybody. Take care.